Hello, in this video I want to provide an intuitive explanation of how gyroscopes and spinning tops work. And the beauty of this explanation is that it can be understood mainly at the high school level. The reasoning can be a bit complex, we have to pay attention, but none of the steps that I will present require any advanced understanding of physics. And we may intuitively understand that the explanation will probably have to do with fictitious or pseudo forces like centripetal acceleration, centripetal force, and other similar concepts. Why is it? Because if you take, for example, a bicycle wheel and you try to hold it by its axle, just put the axle on your finger and put the bicycle wheel there and it's not spinning, it will simply fall. It will pivot gravity, it will exert a force, there will be a torque and it will fall like this. Now, if you do the same and you spin the wheel really fast, or at least fast enough, and you do the same, you just put your finger there to hold the wheel on the axle. First, the wheel will not completely fall. It will just be at an angle with the horizontal, just a small angle, but it will not fall completely. And it will also start rotating around the vertical axis here. And the same applies for two spinning tops. If you have a top and you don't spin it, it will fall. But if you spin it, it will stay upright but at an angle and it will start rotating about the vertical axis. And the main difference between these two situations here is mainly that here you have rotation. You have two rotations. You have rotation in this plane and you have rotation in this plane. So we might have a good idea of the reason why these the wheel stays upright or almost upright is that it has to do with the frictional forces. There must be something to do with centripetal acceleration, maybe Coriolis accelerations, we don't know, but there's something there. That's the main reason. And traditional explanations for this can be found first at a very high level in Euler's equations. So these are equations that describe the movements of rotating bodies. They are very complex. They're usually seen only in advanced mechanics course for physics major. Another explanation that's often presented is that basically if you're doing vector calculus physics, the torque on an object is equal to the derivative of the angular momentum with respect to time, and the torque here due to gravity would be in this direction. The force of gravity is this direction, sorry, and the torque would be in this direction because the distance with the pivot point is here. I'm just presenting that to show that this exists, but I will come to the simple explanation after. Just to make the video a bit more complete and self-contained. And here, so the torque would be in this direction and the angular momentum is kind of in this direction, which means that we want to turn the angular momentum and we will rotate this. If you've never seen this explanation, don't worry about it. It's just, you can look it up online. Or you can, maybe if you want a video on it, just let me know in the comments and I can make a video on this specific point. This video is about a force explanation and basically using pseudo forces. And I'm using a great inspiration from this article, Precession Intuitively Explained by Hantz et al. 2019. There will be a complete citation in the description. And this article can be accessed online for free. It's an open science document. Now on to the next board where I will present how this works. Okay, now let's see how this works. Basically, the idea is that you will take something that's very complex like a spinning wheel, and it's hard to really understand what's going on because as these things rotate and also precesses around this axis, many things happen. Like this, let's say a small point here on the wheel will in a small amount of time move this way, so it will move downwards, it will may move left or right, and also it will move due to this way, it will move this way. It's moved in 3D, and it's really difficult to understand what's happening here. So what we do is we take the wheel first, and so imagine this is just a heavy wheel that's rotating about an axle here, and it's held a certain distance by a pivot here. And what's happening, we will replace the wheel here, the mass of the rim, by a tube filled with the liquid. So far nothing changes, it's still a mass, it's rotating, nothing happens. But now instead of rotating the tube itself, what we will do is we will hold the tube stationary but rotate a heavy liquid inside the tube. And we will presume that everything but the liquid has negligible mass. Now here it's just an approximation, it's a way to understand how things work. It's an idealization, of course, it's not engineering. The idea is to simplify the situation enough that we understand how things work. Now, what we do is imagine you have this liquid circulating in the tube here, but basically it's the same, because here you had something that was heavy, a heavy rim that would rotate quickly, so that would turn in a circle, and here you have some liquid that turns in a circle. So we would expect that not much changes from here to here. But it's still a complex situation. So what we will do is, a first step that seems pretty absurd, but what we will do is we'll change the circular tube to a square tube. Because we want to do another step after that. Here it becomes more complex because we're starting from a circle, which is pretty simple to describe, to a square movement of the liquid here in the tube. And after that, what we do is we bend the top and the bottom part so that it has some radius of curvature here that is equal to the distance from the pivot point. So basically what we're doing now is we have the liquid in each leg of the movement follows a simple movement. In the top leg here, it just follows an arc of a circle. Here it just goes downwards. Here it follows another arc of a circle, and here it goes upwards. And now we can concentrate on this, because instead of having complex movements in 3D, all we have is a movement in an arc of a circle. And we will presume for the moment that I don't know what to call it, but this new shape here is not tilted, it's vertical about the rotation axis here. I know it's another idealization, but we can do everything by tilting it, but it's much more complex. Calculations become very difficult to make and we lose a bit of understanding. So now we take this shape here and we look what's happening. I removed the spokes here. We just imagine it's suspended by like magics, but could be magnetic forces, do whatever you want, but it's still suspended in space linked to this axle. And all we have is we have a very heavy liquid that follows this path. Now we know that this thing has a mass, so there's a gravitational force on this object, which will tend to get this object to pivot about the pivot point here and just basically fall down. But we know that if we have this liquid rotate around this shape very quickly, we have a situation analogous to this wheel here, and we should be able to explain why it doesn't fall. And the explanation, as I mentioned at the beginning of the video, is simply that here we have some movements of rotation of this liquid here. This liquid here rotates with respect to the pivot point here, and this creates fictitious forces. And what's important here is that we know that this shape has to do a precession movement, so it's got to rotate in this plane, and at the same time the liquid moves. So with respect to the lab frame, to the initial frame, the frame basically of the board, if you want, in this part of the movement, the liquid is going a bit slower because it's going this way at a certain speed v, but the whole thing is rotating in the other direction. So this is an inertial frame, and it will cause here the speed of liquid in the inertial frame to be a bit lower than v. We call it v minus, we can call it u, and we will just determine what u is later. Here we have the same speed in the bottom part, but now the speeds add up. So we have V plus U. And of course, the speed of the fluid in the whole loop is a uniform V. So what's happening here is that this liquid here will cause a centrifugal acceleration, if you want. It will cause this part of the object want to fly outward. Just like if we have a rope with the mass, and it rotates like this, and the mass has a certain speed this way, it will want to go out. It will exert a tension in the rope, and there will be some frictious force that wants to pull the mass away from the center and will cause tension here in this rope. Now, here we will have the same. So here there is this part of the tube wants to fly out this way. This part of the tube also wants to fly out the same way. However, here the speed is faster. It's V plus U, and here it's V minus U. So the idea is that here the apparent force that will pull on the old device, similarly to the force that pulls on the rope, will be larger than here. So what happens if you have something that's held here in the middle, and you have a pivot point here, and you pull harder on this region than this region? What will happen? Well, this region will remain upright if you adjust these two things appropriately. So we can see that the reason why the gyroscope or the spinning wheel doesn't fall is because of the differential in centrifugal acceleration between the bottom and the top part of the wheel. And that's basically how it works. So now we have this idealized situation, and we can just revert back all our steps and say, well, what will happen? It will be the same here. Here you have this particular point, and here you have this point will be going this way, we will be going this way, but in the lab frame, in the frame of the board, if you want, this speed here will be a bit smaller than this speed, and this causes a torque that will maintain this wheel upright. And another thing we can get from this qualitative understanding is the relationship between the period of this movement, which is the precession movement, and the period of this movement, the period at which this wheel rotates, TR if you want. And we know that the precession period goes to 1 over TR. That's a result you can get when you do the exact calculations. And we can get this relationship from this model because we know that the centripetal acceleration, or centripetal force, if you will, in the upper part and the lower part of the device goes as, well, the speed squared divided by the distance, but since the distance is fixed, we don't care about it. So in the top part, it will be V minus U squared, and in the bottom part, it will be V plus U squared, because that's the speed here. But if we expand this, we see that it goes at V minus or plus 2uv plus other terms. But the speed v is the same for the upper and the lower part. And what's important is the difference between the two forces, which will give us the torque about this point, and we see that forces up minus forces down will go as 4uv. Because these terms are the same, they will subtract these terms also the same. And what we're left is 4u times v. But u and v are related to the periods, because if the period goes down, so the time taken to travel this shape goes down, then the speed here would go up. And if the period to go around this circle here goes down, well, the speed will go up. So there's an inverse relationship between the two. So the fact that there's an inverse relationship between the two speeds means that there is an inverse relationship between the two periods. And we know that this difference here, which is related to the torque required to maintain this thing up, must be a constant, because the gravitational force is the same. If you don't want the thing to fly off in either direction, we need this force to remain, this difference in forces, to remain the same, whatever these two speeds are, which means that these two things are a constant. Which means in turn that the product of 1 over dp 1 over t precession, t rotation, equals a constant. I would call it K2 if you want, another constant, because of the inverse relationship between the speeds and the periods. So this product is a constant, which means that we get Tp goes as 1 over Tr, which was the result we obtained. If we do the exact calculation. So here you go, you have it. The reason why the spinning top stays upright and the bicycle wheel, the gyroscope, stays upright is due to the pseudo forces that are created due to these two rotational movements, which in turn create internal forces inside the bicycle wheel that maintains it upright. And that's it for today.